we're going to use the definition of the directional derivative to calculate it. So this will be an example of using the definition, and as kind of my typical, you can read it in your boring linear fashion here, but I like to stop and highlight and point out things. We have a function z equals f of xy. It can be modified for more variables, but we're going to only manually calculate with the definition a two variable case. And u is a unit vector, so I just want to put a little note here. Make sure you use your vector notation with your vectors. It won't be too much longer before we're going to use the letter u both as a variable and also for sort of the traditional substitution and an integration. So you got to be able to keep your u's straight. So this one's a vector, and I'm using my typical component form, but you can use other notations for types of vector ways of writing them. So that'll be u1 and u2 to represent the two dimensions that are input. So we're going to take this for a test drive. We're making adjustments to x and y, but the adjustments are getting smaller and smaller as t goes to 0. That's what's happening. And we're trying to determine what happens to the change in the function, which is z, as these little increments in a direction get smaller. So let's see what happens. The instantaneous rate of change at a point on a three-dimensional surface. So here is our example. What you guys think of it? I don't plan on sketching the graph, and I can tell you when you do meet the shortcut for the definition, the shortcut isn't as memorable as the derivative of x squared is 2x. It's a little bit less catchy, but it will definitely be shorter than the definition. So we have a function and we're trying to find the directional derivative of this function at a particular point. 1, -2, so it'll be more of a numerical example in the direction of -3, 4. Limit t approaches 0. Have you seen the problem yet? I'm going to keep writing for just a moment longer. Okay, t is in the denominator. F of 1, that's the x value. Oh, yep, I better tell you in case you haven't seen it yet. You see the issue? This is my direction, my vector. And if you recall what's happening from the previous video, y-axis and x-axis, I'm going to go left 3 and up 4. So we'll say like that. Direction and magnitude there. If I move that direction from my top view, the question is what's happening in the third dimension. Am I going uphill? Am I going downhill in the z direction? Is the slope perhaps 0 and it's level there? But this is not a unit vector. Oh no. So this happens quite frequently when we're in a hurry to get the answer, but we don't take the time to think about the details. It's like having to run to the hardware store again for more parts because I didn't plan well on my first trip for the project. So let's just put a little note here, unit vector. The magnitude of this vector, -3, 4, happens to be 5 because I was being generous in this example. I typically, in my own class assignments, will make sure the magnitude isn't too large of a number if you're doing it by hand. But it might be the square root of 3 or the square root of 11. It could happen. So that means the unit vector is going to be, so that's first So then the next thing we get is the unit vector, which would be negative 3/5 and 4/5, and that, my students and my visitors, would represent the u1 and the u2. The unit vector has the direction that we need for our directional derivative. We need the direction, but it doesn't have a scale that impacts it. So it's sort of like saying if I went one step over, how far would I go up and down? That would be a way of interpreting it. So minus 3/5 t, comma, the y value is negative 2 plus 4/5 t minus f of 1 comma negative 2. Now we're about to find out that my paper isn't wide enough to handle this, partly because I filled in my scratch work here. Again, this is not uncommon. So instead of making it, trying to squeeze it in here, and maybe you can read it, maybe you can't, I'm just going to sort of migrate down the page slightly and see if I can't do it this way. Limit t approaches 0. If I have every x component is 1 minus 3/5 t, and I substitute or quote plug it into my function, I will get in the numerator here 1 minus 3/5 t squared minus 5 times 1 minus 3/5 t, and the y value that's right here is negative 2 plus 4/5 t plus 4/5 t. So that's what I get when I substitute this into the function, minus what is f of 1 comma negative 2. 3 times 1 squared minus 5 times 1 times negative 2. Notice lots of parentheses. I do the extra parentheses here to not create errors in minus signs. When you have that many minus signs stacked together, if you're at this level of mathematics, you get it and you'll convince your brain that you can just do this. They tend to be the more common mistakes and harder to find because we just assume we didn't mess up there. Alright, so that was equal to this. Let's keep going. Now I'm going to do my multiplication perhaps a little bit more quickly than you would prefer. So remember to pause as necessary. Let's see what happens here, if I can make this work. 3 times 1 squared is 1 minus 6/5 t plus 9/25 t squared minus 5 times 1 times negative 2 is negative 2. 4/5 plus 6/5 is 10/5. Yes, I know that reduces, but trust me for a little bit here. Minus 12/25 t squared. Okay, so I could just determine what this number is here. That's 3 plus 10, that would be 13, I guess. So I'm going to subtract 13. All divided by t. Okay. So equals limit t approaches 0. So I would say that we're almost to the point where you're going to see that we're going to go downhill now. This is like climbing uphill algebraically. This should not be difficult, But again, I might have gone too quickly, and it might still be categorized as annoying. So we're going to have here 3 times 1 minus 18/5 t plus 27 over 25 t squared minus a negative would be plus 10 minus 50/5 t, because I'm eventually going to want to combine these together, so that's why I didn't reduce the fraction. Minus a negative is positive 60 over 25 t squared minus 13 divided by t. Okay, 3 plus 10 minus 13 is 0. Every term remaining has a factor of t in it and can be reduced. Again, this isn't in Calc 1 or before calculus where you were kind of more obligated to show every step, but I would always caution you, if it looks easy and you do too much in your head, don't make the errors. Go slower. Be correct the first time. Limit t approaches 0. What do we got cooking here? Well, I got negative 68 over 5 t reduced plus 87 over 25 t, because I combined those terms but I reduced by one factor of t, and if t approaches 0 I get negative 68 over 5. Now, what does this mean? Well, that means x and y axis. Z-axis is coming off the paper. If I go in the direction of the vector u, my z value is going to drop by almost 14 units. It's very steeply negative if I were to go in that direction. I think you will find that if we were to go in the opposite direction, it would be the same slope but in a positive number. Maybe you could figure out a way to change the vector to try that out. Would you get the same number but positive? What you should do is go back to the original problem make minor modifications to this polynomial, or make minor modifications to this vector. Make it so the magnitude has a small square root in it. A small square root, not a very large square root, just a small square root in it. And try to use this definition yourself. Can you do the initial substitution into the function? Can this step down here? Can you do that initial substitution? How's your multiplication, sometimes nicknamed FOIL in the Western world? How's that going for you? Ultimately, to get to a number. Now, I shouldn't say ultimately there. We would get to a number using this process if I gave you a point to work with. What we'll do next is try to, well, I won't hint at it. We're going to meet the shortcut. We won't linger too long on the definition, but we're going to meet the shortcut. You'll find the shortcut is shorter, but not instantaneous like the power rule was. So, I will see you next time.